All right, guys. Question was asked about number one here. This is on the 2022 AP test. So as I'm doing this right now, this was batch number one of homework here, guys. So what's going on here? This is what we typically would call an input-output problem, which shows up very frequently on the AP free response questions here. So what's going on? From 5 a.m. until 10 a.m. right here, the rate at which vehicles arrive at a certain toll plaza is given to you by this function right here, A of t. It's important to read this, guys, where t is the number of hours after 5 a.m. And then this is important here, too, I think. A of t is measured in vehicles per hour. That means that this function here, guys, is a rate. Vehicles per hour would be most similar to maybe a velocity as opposed to vehicles, which would be like a position, or something like vehicles per hour, which would be like an acceleration. This last sentence is interesting. Traffic is flowing smoothly at 5 a.m. I'm not really sure that that's important, but this is important here, and I think that's why they gave us that first part. No vehicles are waiting in line. That right there, everybody, is what we would call an initial condition, and when that initial condition is 0, you can very often get away with ignoring that. But I'll warn you guys that on a ton of these problems, there is an initial condition that you do have to worry about, so I always think circling that is a good idea. Okay, let's get started right here. Part A is asking us to write but not evaluate, thanks guys, an integral expression that gives the total number of vehicles that arrive at that plaza from t equals 1 until t equals 5. And this is where units are going to help you guys out. This A of t function that we were given right here, we said just a while ago, is measured in vehicles per hour. We want the total number of vehicles that are going to arrive then. So how do we go from a vehicles per hour function to vehicles? That's what a definite integral is going to be for here. We're going to do a definite integral here starting at t equals 1 and ending then at t equals 5 of that A of t function. And since that A of t function is already written for you on your paper here, there's absolutely no point in writing it out again. We'll just call it what it is, A of t, and then we're taking that integral with respect to t. And let's think for just a second, guys. Our integrand, A of t, is measured in vehicles per hour. We're then multiplying that by dt from 1 to 5 hours. So we are multiplying right here vehicles per hour multiplied by hours. The hours cancel, leaving us with vehicles overall. And that's what we wanted for part A, and for some strange reason, they must have thought this problem was a little bit too time-consuming here. They don't want us to go ahead and evaluate that. They said just set up the integral and then leave it as is. So that's my answer there for part A. Okay, B is asking us now to find the average value of that rate. And I'm hoping you guys recognize this phrase right here, average value, as a formula we should know already. So the formula for average value of any function that we've talked about this year is going to be 1 over, so we all understand, 1 over b minus a times the integral then from a to b of whatever the function was, f of x dx. I did all that in red because let's go ahead and just dive in and do it for this problem now. The b and the a values are, again, 5 is the ending value, that's b, and 1 is the a value at the start. So this would be 1 over 5 minus 1 multiplied then by the integral from a to b, 1 to 5, of, well, what are we finding the average value of? The rate at which vehicles arrive. And that is exactly what this A of t function right here was measuring. So we're going to put A of t dt measured right here. So this integral here is identical to what we just talked about in part A. That'll give you the total number of vehicles that arrive from 1 hour to 5 hours, but then we divide that by 5 minus 1, which is in hours, and that gets you then, let's see, back to vehicles per hour, which is what they're asking for here. So we need to go to our calculator here, and anytime you're doing a problem like this, guys, on the calculator portion of free response, if they give you a function, it is almost always to your benefit to define that function. So let me go to Tools and Actions and Define here. And we will name this function just like they did. A of, oh, where's my t hiding? There it is. Okay, A of t is equal to, and this was 450, and then multiplied by the square root, so here you go, of the sine, gotcha, of 0.62, and that got multiplied then by t, and that should do it for defining the a of t function. Now we're going to go ahead and type in this integral that we just wrote out. So I'll do that as a fraction just so it looks a little cleaner. That's going to be 1 over 5 minus 1. And of course, you could just put the 4 right there. We're going to multiply now this by, let's go back here, calculus menu 43 for you guys, the integral from 1 up to 5, and the integrand now is just going to be that a of t function that we typed in just a second ago. And we're going to evaluate that integral with respect to t, and that should be what we need, guys. I'm pretty sure that is what we typed in there, and we got 375 point. Reminder, everybody, we're always going to round to 3 decimal places unless the directions tell us to round somewhere different. So I think it's going to be 375.537, unless I go back and read. Doesn't say anything about rounding, so let's go with that then. 375.537. The problem did not ask us for units. Well, actually, they gave you the units already, vehicles per hour. But if they don't ask for units, we don't give them to them. Okay, so that's part B. Moving right along, let's get into part C and see what we're doing here. Okay, is the rate at which vehicles arrive at the toll plaza at 6 a.m. or t equals 1 increasing or decreasing, and give a reason for your answer. So let's think big picture, guys. A decent amount at the end of the first semester, this was back in December, we talked about what it is that determines whether a function is increasing or decreasing. And the main thing they want to know on the AP test is, do you understand how the first derivative of a function impacts that answer? When a function's first derivative is positive, that function is increasing. And when its first derivative is negative, that function is decreasing. So they're asking us now, this gets a little bit confusing here, is the rate at which vehicles arrive at the toll plaza, that is what's given to us by a of t. Is that function there increasing or decreasing at t equals 1? So what we're going to need to know here, guys, is what is the value of a prime, the derivative of a, evaluated at t equals 1? And this is something I didn't have you guys do a ton of during the year, but it's almost assured to show up once or twice on the AP test. You can use your calculator to evaluate numerical derivatives. We don't need to come up with a prime of t by hand and then plug the 1 in there. So let's talk about how to do that. All right, guys, for you, you're going to go to your calculator and you're going to type menu 4 for calculus, and then we're going to hit number 2 here, which is derivative at a point. Now, the variable by default is x, but I called this one t, so I better go back and change that. The value at which we want the calculator to evaluate this derivative was t equals 1. And if we were looking for a second or a third or a fourth derivative, okay, but no, first derivative is what we're doing right here. So let's hit OK, and it opens up this for us. So the calculator is going to evaluate the derivative with respect to t of, well, we need to tell it what function now. And that, again, is going to be a of, I lost it. There you go. A of t. There you go. And then at the end of all that, there's a bar here, meaning evaluate that derivative at t equals 1. So when we hit enter here, I got this number. I really could care less about the numerical value. All I really care about is the sign. But I'll write it down just to show them that I know what I'm doing here. 148.947. Let's write that down. 148.947. And now let me make a really obvious statement, which is greater than 0, meaning that it's positive. So if the derivative of a function is positive at a particular point, that means that our function is increasing. So the directions did say on part C, give a reason for your answer. So I think we can say right here, sure, it doesn't really matter what order we do this in. Since a prime of 1 is positive, greater than 0, then the function here that a of t, we would say, is increasing. at the value t equals 1. And I think that's about as much as we need to say here, guys. Kind of said it in a full sentence right there. The function is increasing, not just everywhere, but specifically at t equals 1, because the derivative of that function, evaluated at 1, is positive. And I think that's all we need there. Now, d is the tricky part to this problem here, guys. And as somebody asked me this question in class the other day, we didn't get the answer quite right, and I think I figured out why that was. So, what's going on here in part D? A line is forming whenever A of t, which is that rate at which vehicles arrive at a toll plaza, is greater than 400 vehicles per hour. Okay, the number of vehicles in line at a time t in between A and 4 is given to us here by this function right here. N of t is a definite integral from a to t of a of x, which is what we would call the input function, everybody. That's the rate at which vehicles enter the toll plaza, and then minus its output function. Now, they didn't really say this here, guys, but what is to be inferred here is that no matter how many cars are piling up, the maximum rate at which the toll plaza can process people and get them out of line is 400 vehicles per hour. So when that happens, that's the function that's given here. And this is the part that I didn't pay enough attention to the first time I looked at this problem, where A is the time when the line first begins to form. So the line forms any time that A of t is greater than 400. We're going to use our calculator to try to figure out when that is. So here's what we're going to do here, guys. I initially had tried to solve this equation on the calculator, but because it's trigonometric, we got some goofy n1s and n2s in our solutions right there, and it was basically saying, hey, there's an infinite number. So what we're going to do here is what actually we used to do back in the day, and it's what a lot of Calc students still do when they're using maybe a TI-84 or a regular Inspire that's not a CAS. We're going to go to a graph, everybody. So we're going to add a page, and I'm going to do a graph right here. And the very first function I want to graph is the A of t function that we already defined. Now, this is just a little bit tricky. I can go ahead and type in A, but I'm pretty sure if I do A of t, the calculator isn't going to like that. Yeah, it isn't going to do that for me. So let me cancel this. What we need to do then, everybody, is make that instead A of x. All right, so what's important to the calculator is that you've named the function a, we're just changing the variable now. So that certainly doesn't look like much, everybody, but okay, we'll do something with that in just a second. Actually, I lied. We're going to do something with that right now. What we're going to do, everybody, is change our viewing window into something that's actually useful and helpful for us. So you guys are going to want to hit menu here, and then let's see here. We're going to go to window and zoom, which looks like it's maybe the fourth option down, and we're going to go to window settings. So let's think about where we're at. X minimum. X is our time value right here, guys, and we can't have a time any less than 0, so we'll put that there. For our X maximum, if we go back and read this problem again, this whole model was only valid from 0 up until 5 hours. So I'm going to go from 0 to 5 and run with that. Don't worry about X scale. Let's talk about Y minimum now. So Y is the value of A here. It's measuring traffic flow. So the lowest your traffic flow could ever be here would be 0 cars per hour. And then Y maximum, the greatest that your traffic flow could ever be, well, this function here, guys, was 450 times the square root of sine of blah, 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 blah. Well, sine of anything has a maximum value of 1. So the highest value this function will ever take would be 450 times the square root of 1, which is just 450. I'm going to go ahead and put a 500 in there just to give myself a little bit more breathing room, but I'm going to hit enter now and hit OK. Okay, and now, boy, that looks like a semicircle right there, but all right, that's where we're at. The other thing we're going to do is graph the second function right here, which was y equals 400 cars per hour. So just a constant function. All right. And what we find right here, guys, is that, well, I wish I could point and highlight things here, to the left third of this graph here, where the red line is above the blue curve, that means that the toll plaza can get people out at a rate faster than people are showing up. So from 0 up until, I don't know, guys, maybe 1 hour, there's no line here at all. The problem is right here in the middle. What did I just do? The problem is right here in the middle, guys. Oh, did I wreck my whole thing that I just did here? Yeah, I think I did. I lost my 400 line. That was the problem. Okay, there you go. The problem is in the middle. Where the blue curve is above the red line, that's when the toll plaza can't process people fast enough right here, so we have a line that's piling up. What's important here, guys, is that we have 2 points of intersection. So we're going to go ahead and find them on the graph, and let's see. To do that, we're going to hit Menu. We're going to go to Analyze Graph, and we're going to find a point of intersection. And my lower bound, oh, shouldn't have done that with my pen. Okay, let's try this. My lower bound just needs to be somewhere to the left. My upper bound just needs to be somewhere to the right. And voila, there's that point of intersection right there. Let me do that same thing again, guys. Another intersection for this point over here on the right. So there's a bound to the left. Here's a bound to the right. And there we go. Now, this is always tricky here, guys. What I'd like you to do now, and I'm not even sure how to do this on the iPad, is to store those two X values into the calculator. So can I just tap on the button right here? Okay, that kind of worked, but now what? What if I held down there? Nope, that didn't work. I don't want that. Tap it once. Okay, what could I do right here? I don't think it would be... For you guys, this is on your keyboard right here. You would just hit the store button, and I'm not sure that I know how to do that on the iPad, everybody. So... no, that doesn't help me at all, and I don't think that helps me at all. So, I'm going to show you guys maybe another way to get around that here. All right, let me go back to the main page here. All right, and what we're going to do is what wasn't going to work out very well, and I knew that. If I go to Menu and then Algebra and then Solve, this is the way I would have normally tried to do this problem. If I solved the equation A of t, gotcha, is equal to 400, and then gave it a comma, and told, where's my comma? There you go, and told the calculator to solve that for t, this is what it's going to tell you, and nobody likes that. So I'll remind you guys of something I'm pretty sure I taught you this year. You can ask it to find a specific solution close to a value. So I'm going to tell it now to solve this for something close to t equals 1. What that's going to do is it's going to give me only one solution here, and the one that's closest to t equals 1. So there's that number of 1.469 blah, blah, blah. So that's what we were kind of looking for. So let me stop right here. Let me go back to my paper. And let me write down what it is that I'm doing, trying to explain my thoughts to the grader here. We want to know when this a of t function is equal to 400. So that occurs at t equals, and the first solution we just came up with was 1.469. Or there's another one now at t equals, and let's do this one again. So I'm just going to hit up, and enter. But now instead of a 1, this one was a little bit later on. I'm just going to guess 4 right here. And here's the solution it gave me now, 3.598. So let me write that down as well, 3.598. So those are the two times right here at which a of t was actually equal to 400. We're trying to find in this problem, guys, let me go back and read this again. We're trying to find the greatest number. We're trying to find a maximum value here for this n of t function, and that can occur then, everybody, at either its critical points or its endpoints. So I probably should have written this down here just a second ago. So if n of t is defined here as the definite integral from a to t of the a of t function, actually I take that back, they changed that to a of x, didn't they? The a of x function and then minus 400, all taken with respect to x, then its derivative right underneath that, n prime of t, would be, well guys, the derivative and that definite integral would just cancel each other out according to fundamental theorem of calc part 2. The only little caveat there is that we replace this variable with this variable right here. So this now becomes a of t minus 400. And that actually explains why I did what I started to write a second ago. You would want to set that derivative equal to 0 and solve. And so you'd bring that 400 to the right, and that would get you a of t is equal to 400, which is what I started working on right over there. Okay, so here's where we are here, guys. Maximum values can occur at either critical points or at endpoints. So we need to test the value of this n function at a couple of different times. Now, the n function begins here at a. And if I went back and I read my directions more carefully now, here's what it says. where A is the time when a line first begins to form. And when does the line first begin to form? At the first time right here where, give me just a second here, guys, at the first spot where these two curves intersect, which is right there at 1.46937, blah, blah, blah. And so what's important about that now that I missed before is that that spot right there is going to be the value that we're going to put in for A right here. And we're going to evaluate it here and here, and I think for good measure we should probably do it at the right end point, which is 4, but there's really no way that could be the answer. So we're going to do t of 1.469, excuse me, n of that. We're going to evaluate n at the second point, 3.598, and then just for good measure we'll do n at the right end point of all this, which is 4. Now to do all that, guys, we need to define the n function in our calculator, which I do not think we have done yet. So let's go, here we go, back right here, and let's define yet another function here, guys. All right, so actions and define, and we will call this one n of t. Okay, gotcha. All right, and that one is going to equal, forgot a parenthesis right there, is equal to, all right, and this got interesting then, guys. We need to go menu, and we need to go, not to tools right here, 43 for an integral here. And it was an integral that started at a, but again, a was that lowest value at which those two curves intersected, which was the 1.469371 blah, blah, blah from before. Normally, I'd have you guys store that one, but the directions in this problem did say to go ahead and give an answer that was rounded to the nearest whole vehicle, so that's not super important that that's 100% correct. That upper limit of integration was just going to be t, all right? So an integral from 1.469 to t of our function right here, which was going to be a, evaluated at, and your calculator really doesn't care. I think we'll put the x there, and then a minus 400, but we're doing all that integral with respect to x. Okay, so that's my definition right here. It doesn't give me any problem with that. And now we wanted to go ahead and evaluate this, although as soon as I did it before, I felt kind of silly. If I were to evaluate n at that left point of intersection, 1.469371, I don't think we should be surprised when we hit enter and we see an answer of 0. If you look at what I have on the second line above, guys, that lower and upper limit of integration are the exact same number. So, of course, that means that at this moment right here, there is no line yet, and we have no cars waiting at that moment right there. But what we think we understood is that in the middle of this graph here, guys, if you remember, this thing looked like a big hump like this, and then there was a horizontal line coming across. In this region right over here, there are cars accumulating in the toll plaza. So it seems to me that this is probably the likely case here for our maximum value. I'm definitely expecting a positive result when we do n of 3.598. So let's try it. N of 3.598, and you know what? Let's type it in right. It's probably good enough right there. All right, 71.254 is what I got. 71.254. Now, how about at N of 4? At N of 4 now, which is actually sometime like over here somewhere, we're now clearing cars out of the toll plaza here at a faster rate than they're showing up. So that doesn't mean there's going to be no line right here, but I do think this line will have gone down from what it was at its peak. And N of 4, yeah, it did, 62.338. All right, guys, 62.338. So let's make sure we've answered the question, everybody. And the question was, find the greatest number of vehicles in line at the toll plaza in the time interval from A to 4 and justify your answer. Now, I'm going to remind you guys that what they said here in part C, give a reason for your answer. They'll sometimes use the word explain right there. Explain, or giving a reason, that involves words. But when they use the word justify, they use a different word right there, because justify does not need to be a verbal explanation. They just need to see the work that you did to come up with that. And we've shown all that work here in what we did right here with our n prime of t, our derivative equation, in setting a of t equal to 400, and then in testing all of these values over here on the left. So let's go ahead and answer the question right here, guys. Let me try to use use their verbiage, the greatest number of vehicles in line. Okay, so I'll abbreviate that a little bit. So the max number of vehicles in line is, and the directions did say here, to the nearest whole number. There you go. So 71 is the answer that we're going to come up with right here for part D. So that's all of number 1. I definitely thought D was the hardest part of that problem. And as I looked at the point allocation right there, I do believe then, everybody, that, yeah, the majority of the points right there came from part D. So that's a tough little problem right there. Hopefully that makes a little bit more sense now that you've seen it. I can pretty much guarantee you will see at least one more, probably several more input-output problems in our prep work getting ready for the AP test, and there's a really good chance that one of these problems is going to show up on the actual AP test you guys take later this year. So we'll see something like this again in the future.